Good morning, everyone. My name is Timothy Lee Grant, and today we are going to be talking about linear regression for machine learning. But before I actually get into linear regression, I want to talk a little bit about what a model even is. What do I mean by my model, and how do I say my model is doing good or my model is bad? Like, what does this even mean? So, a model is going to be some equation or a transformation that takes in input, brings this input in, okay? Then it transforms the input in some way and creates a prediction. So it takes in input, transforms this input into an output, and that output is a prediction. So for example, we can have the square foot of a house, and then we want to predict the price which this house will be. So the input is going to be the square footage, and this number is going to be fed into our model, and the model is going to transform it in some way as to produce an output, and that output will be the prediction. It will say how much it thinks the house is going to be given the input which it was given. Okay, so let me go and just write a model on the board, okay? So here we go. So here's the two axes. The y-axis is going to be our prediction. The x-axis is going to be your input. So our input, we said, is going to be the square foot. Square foot, okay? And then the output, we said, is going to be the price. So, there we go. Now, let's create our model, okay? There we go. So this is a model. This is our model right here. This line, okay? What is it doing? It is taking every point on our input. For every input, it is giving us a prediction. So we feed in to the model that we think that the square foot is going to be, we feed into the model that our input is going to be, so we say at this point right here, this is our input, and this is just a number, right? This is how the square foot, let's say it's 10 here, 10, okay? What is our model saying? Our model is for the input 10, it is here, and our output is right here. Dot, 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 dot. Like that, right? So whatever this number is right here, let's say it's 50K, right? So this is a model. It is taking in an input and giving an output. It is a mapping between inputs and outputs, okay? This is the output, this is the 50K, or this is the price, and this is our input. And notice for every input, bam, 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 no matter what I choose on the input axis, there is a corresponding output, okay? Now, this model right here, we can say is governed by an equation, right? Let's write this equation here. Y equals x squared, okay? This is a parabola, right? So the x-axis right here, we can feed in an input right here, and here is the transformation which occurs, correct? This transformation takes in the input and feeds an output. So we have our input goes here, it comes and gets transformed here and has a corresponding output. This y is our output, okay? So now we can make things a little bit better, all right? Say equals, and then mx plus b. All right, well, this is our normal equation, which we learned a long time ago, right? Let's just look at it and see what's going on. Well, here's our input right here. So we'll take in some number, right? We don't get to choose what the input is, right? We are given our training data, and that is what goes in here, is the training data. Now, right now, we only have one input, which is x. Okay, there's only one input. We don't get to choose what the input is. This input also is when we are asked to give a prediction, right? We don't get to say, well, I want to predict on this. No. Our model needs to say, okay, well, given an input, a valid input, for example, what I mean by valid is for square foot, it doesn't really make sense to have negative square foot, right? So we can restrict what a valid input is, but for our valid input, we need to be able to come up with a prediction, right? So here is just a single input. Now it gets transformed, it comes in, and this is maybe, we said it was 10 right here, right? 10, and then multiplied by m, and then you add b, okay? So the m, this is going to be a linear model. So we have some kind of thing right here, right? The m controls the slope. So rise over run. If m is 2, we're going to have 2 up and then 1 over, and then it's going to be like that. Okay? Then the b controls the shift on the y-axis. So if b is 2, we're going to go up 2 right here, and this is where the intercept is going to be. So 1, 2, and then draw our line like that, okay? And now we can keep looking. This is a mapping between all of our inputs, and it gives a corresponding output. So here, and this would be our prediction right there. Does that make sense? Okay, so now let's add some training data, and we can start talking more about the linear model for machine learning. Okay, all right. So we have something like this, and now each one of these points is a training data. What does that mean? All right, let's go back to concrete. What does it mean? What is this guy right here representing? So that is an individual house. So we went out into the world and we measured a whole bunch of different houses, and we said, okay, well, it has a square foot of this, and it is a definite number, right? This is a definite number. This is going to be some square footage. So we measured house is this square footage, and we also measured the price, because remember, this is training data. So for training data, you have both the inputs and the prediction, okay? That's how you learn, is you need training data that has both the inputs and the outputs, and that's how you learn how you create your model, which accurately predicts how to map between the inputs and outputs. So we have, this is a specific house. It has a specific square footage and a specific price, okay? This is a specific house. It has a specific price, or specific square footage, and a specific price. So each of these are individual houses, okay? Each of which have the input, a specific input which is known, we are given that. and the corresponding output, the corresponding prediction. Okay, so now let's do a linear model to fit this data. There we go. Here's my linear model. It is linear, right? It fits the form y equals mx plus b, okay? B is going to be this, right here. Here's b. And now the slope is going to be m, which in this case will be negative, right? M is going to be some negative number. So what does this mean? Well, let's look at it. What is this model predicting? Okay, for any given input, here is going to be the corresponding output. Now, this isn't a very good model, obviously, because why? Our model does not follow the data very accurately, correct? It has a high error rate. And we'll talk more in the next video about what error actually is. So let's go around and let's actually try to fit this a little bit better. Let's adjust the parameters. So, as I mentioned last time, you don't have access, or you cannot change the x. You are given the x. The things which you can change in your model are these two things, the m and the b. So, looking at it, right, this is probably a better model than the negative one. Well, let's keep changing m, and let's keep changing b. Maybe that. We changed m more. Well, then if we shift down b, we'll get something like that. And that seems to do pretty good. Okay? So we just manually trained our model that we adjusted these parameters in order to best fit our data. And that is the entire idea behind linear regression. You change your parameters in such a way as to predict most accurately. So you try to minimize your error over your data set. Okay? So that's the idea, but this is only one dimension or two-dimensional. You have one input and one output. Two-dimensional. But we can make it three. Okay, so this is one input, square foot. If we had another axis coming out, and that one was temperature. So you might say that there's a correlation between the temperature and the house price, right? Houses in California go for a lot more than houses in Alaska. So we would have another axis, and what would our linear equation look like? Well, we would have mx1 plus dx2 plus b. Okay, so m and d are just different weight vectors, or different weightings, right? These control, the m controls the slope on the x1 axis, correct? So here's x1 is this way, and x2 is coming out. So the m will change this slope, and the d will change this slope. Okay? So let me rearrange this formula a little bit. Let's just, instead of calling m, let's just call this weight 1, weight 2. Okay, well, that looks a little bit better. I don't really like that b, but we can change that as well. We can just go 1 multiplied by weight 0. So what's going to happen is we can change our weights, and this will just be the 0th weight, right? So we have a vector, and it will be weight 0, weight 1, weight 2, dot, 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 dot. for however many dimensions that we have, weight n, and each of these will control the slope in their respective dimension, okay? And weight 0 is just going to be some shifting. All right? So now, in 2 dimensions, we said that there's another axis that comes out this way. And now our model is no longer going to be a line, but this takes a little bit of imagination. If we have an axis out here, here is going to be our input space, okay? What does that mean? That means we have an x1 value given by here, and then an x2 value here. And on this space right here, it corresponds to a given input in x1 and then a given input in x2. And now right here is some point, correct? And we can move it anywhere along this flat surface, which is our x1 and x2, okay? Now, corresponding on this surface here, there's going to be another surface that comes maybe like this, okay? And what is the surface above it? Well, that is the mapping between this 2-dimensional input space and the prediction. So what do? For any input on this 2-dimensional input space, there's going to be a corresponding output, all right? Just like right here, input, input, on this 2-dimensional input space, we have a transformation which takes in the inputs and gives out a prediction. All right, so we talked about how we can have multiple dimensions. We can have the x1 dimension, the x2 dimension, and how they're governed by weights. So how is this actually represented in our machine learning model? So what we do is we have what's called a vector for the input. So this is given to us. So what we're going to have is actually a matrix, okay? So here is our input right here. And what this is going to have is each of these here, 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 each of these is going to be an input. So this is going to be x1, x2, x3, x4. So each of these is a different dimension. So we go up to xn, if n is how many dimensions there is, okay? And then each of these is going to be a different training example, okay? So this first one, corresponds to this first one here, right? So it's going to have, this x1 is going to be its x1 value, this x2 is going to be its x2 value, and then there's no reason that just because we can't visualize it, right? We live in a 3D world, but just because we can't visualize it doesn't mean we can't have x3 and then an x4, x5, x6. It's going to be more dimensions, but the computer, there's no reason why the computer can't do it, right? You just add more dimensions here. Math works out, no problem with the computer. So even though we can't visualize it, we can just have in dimensions. We can have as many dimensions as we want, okay? So that x1 is this point's x1 value. Then this one is this point's x2 value. Maybe it's right here, right? Then it's x3 value. And then these become kind of hard to actually visualize, right? But this is for the first training point. Then the second training point, third. And this is, I think we said that there was like 15 training points or something like that. So this is the 15th training point, okay? So this is how we actually represent our input. This is our training input. Then we will also have y1. So this is going to be our output. So what is that saying? for this training data point right here, so this first one has this x1 input, this x2 input, this x3 input, and its prediction, or its output is y1. The second training data point has this output, So each of these, this is one of our training data points. That's this one. This y2 is going to be this one, and that's this right here. Don't forget, this one is our output, correct? So the first one is this value right there. The second one is this one. So right there. Then third is the third training point's y value. The fourth training data point's value. So that's, you have a vector right here up to y of 15 if there's 15 training points, right? And so this is what's given to you right here. Okay, you were given this. Now, what you need to do when you are creating your linear model? Well, you need to multiply. This is, right here, the equation which is called linear. And what does that mean? That means for each of the inputs, it is multiplied by a single scalar value, right here. So W1, W2, and in this case, we would have up to n. So we would add more. We would have plus W3 x3 plus W4 x4, like that. We would have multiple things, right? Okay. So now, what will we have to do? We have to create a W. We have to create a vector, which is for every input, every one of these inputs, for every single dimension, right? We will need to multiply this number by some weight vector. So how do we actually do that? Well, the way that we do that is we will have, I'm trying to figure out where I should put it, possibly right here maybe. So we'll have a weight 1, a weight 2, a weight 3, ... and then a weight n. So there is n many. Okay? So what are we going to do? We need to multiply this weight 1 by this x1. This weight 2 by this x2. So we want each of these to multiply with its corresponding x1 with w1, x1 with w1. We want these to multiply and then add together. Well, if we remember from our linear algebra, the way that we do that is we go like this. Do you remember matrix multiplication? You have like this, right? So we want to multiply these corresponding and add it. Okay, so actually, I don't want this to be x1, x2, x3, x4. I don't want this to be a row because I want to multiply these, right? I want to multiply it this way. So I can just transpose this big matrix, and what am I going to get, right? Let's just transpose it, and we'll then later show more clearly how the matrix operation actually works. But so if I just transpose this matrix, all I did was just transpose it, right? Such that I get x1, x2, x3, ... x4. I transpose it. Now, each of these are the corresponding inputs. Okay, so x1 is still this, x2 is still this one, x3, x4, all of these up to xn, okay? And now each of these columns is a different training data point. So this is for the first one, this column is for the second one, this column is for the third one, fourth one, okay? So now I have this. Now, okay, like this, I want to multiply this W1 with this X1, okay? Well, that works, but the dimensions don't work because I'm going this way on my multiplication for this W1. I could transpose this one too, can't I? Of course I can. So I'm gonna transpose it. W1, W2, W3, Wn. Okay, so, starting to like this. Oh boy, I like this one. Like this. What does the matrix operation for this look like? W1 x1, okay, plus W2 x2 plus W3 x3. Oh boy, up to Wn xn. Oh, that's perfect. That's just what I wanted. That's just what we have up here. W1 x1, W2 x2, and everything is added together. That's exactly what we have. All right. Well, does it work for the second instance? Well, before I have that, okay, so what does that mean? Okay, so we just did that. X1, W1, these are multiplied. Then you add this. Then you add the multiplication of this, right? And then you multiply these two and add it, just like we have up there. What is that going to result in? That is going to result in just a number. Just a scalar number, right? That's going to equal like, oh, it will be... this will come out to be some number. It's going to be, why don't we call it Y1? It's going to be some output, right? That's what it is here. It's an output. We said we take in this input, we do this transformation, this linear transformation, and it gets an output. And this multiplication and addition, that's just the matrix version of actually creating this equation right here. So that should correspond to our linear model, okay, for this given input x1, this given input x2. And now if we remember, this training point is what our model is actually trying to predict. So we have here what our model is going to predict. So this is what we want to be very close to the actual predicted value. Okay, so now let's look, does it work on the second training data? Well, remember, we go like this, okay, then we go on this one, and then we go like this. And it's going to do the exact same thing, right? W1 multiplied by x1, and by the way, these two are different. So this is the first training data point, that's this one. This one is the second training data point, but it's for the x1 dimension. And this second one's x2, this second one's x3, and this one right here will be the third training data's point, x1's dimension. This will be the third training data point, x2 dimension, etc. So we just multiply it along here, and this is going to be some number. It's going to be an output, right? So I'm going to say, when we do matrix operation, it goes this way, and we get a scalar value, okay? So I'll just put O1. That way it's different than this. This is our actual value. This is given to us. O1, so we go bam, and then bam. Okay, so now we have O2, O3, and then we have an output for however many data points we put in, right? Each of these is going to come out with one output, one output, one output, one output, one output, all the way, however many. Let's say we have 15, so we're going to have output 15. We can make that into a vector, and this will be a vector of our output for our model. So we have our training data points, we have our weight vectors, and then we multiply it this way and get an output. We multiply it this way, get an output, this way, get an output, okay? And we want this to be very close to the actual, right? Just like we wanted here. We wanted, if I plug in this input, I really want my model to be very close to the actual output, right? So in the next video, we're going to talk about error and how you actually do that. But the only thing that you're allowed to adjust is your weight parameters. Weight 1, weight 2, weight 3. You can adjust these, and you're trying to get your output to be as close to the input, you're trying to get your output to be as close to the actual output as you can. And that adjustment of these weight parameters is how you learn. That is how you learn your model. Remember how I said the model is essentially the equation, okay? You don't get to choose your inputs. You get to choose your outputs. So here, bam, this action of multiplication, so this multiplied by this, plus this multiplied by this, plus this multiplied by this, will result in some output, just like we did here. This multiplied by this, plus this multiplied by this, plus this multiplied by this, will create some output. And this is our model right here, and we can adjust those. Does that make sense? All right, thank you guys so much for watching. In the next video, we're going to formalize what error actually is. And then once we have an idea of what error is, then we can try to change these weight parameters such that our model predicts much closer to the actual value which is given in our training data. So that's upcoming. I hope to see you guys then, and in the meantime, have a wonderful day.